So thanks a lot. Thanks for the invitation, and thanks for the opportunity to share some of the research that we're conducting at the University of Stuttgart here, which may offer you some outlook of where we may go in timber construction. So maybe one wonders, why is construction important? And for that, we may have to have a brief look at the bigger picture. So I think we need to understand that construction and the building sector is actually facing one of the grand challenges of our times. According to the United Nations, we actually need to build an additional 230 billion square meters of cross-floor area until the year 2050. 230 billion square meters is about the same area that all existing buildings on the planet currently have. So we have to build all the buildings that you know again. The example that is given in the United Nations Global Status Report is that means we have to build the city of Paris again every 3 weeks, and then again and again and again for the next 30 years. And that also includes Europe, where we expect an additional 15 billion square meters of floor area to be constructed until 2040. However, already now, we know that building construction causes a severe environmental impact. Actually, the building sector consumes 40% of global resources and energy, produces 38% of CO2 emissions, and is responsible for 50% of global waste. On the other hand, of course, there's a big opportunity. If you imagine what kind of volume of construction we're facing, and we need to bear in mind that already now the building industry is actually the largest industry sector worldwide, with the predicted enormous future growth. However, the productivity has been stagnating for decades. Actually, has been declining recently. In the end, when we talk about construction, we should keep in mind that we're building the world in which we actually live. So in the Western world, we spend 87% of our lifetime in buildings. So those are the human artifacts that have the biggest influence on our quality of life, and of course also stay quite long with us. So we should take utmost care to design them with the best possible quality. So now, of course, timber construction can help actually address a lot of these challenges, especially if kind of combined with digital technologies. So how do we deal with digital technologies right now? I think what we all aim at is a kind of digital chain. So there's a lot of effort in how do we make sure that data is passed on from one stage of design and construction to the next. But if we look at it, we also have to understand that what we're doing is we are digitalizing design and construction as we have done it in the past. So if we look at the current digital methods, and of course they're really important, but in the end, they are digital methods for essentially pre-digital design approaches. Similarly, if we look at automated fabrication, and of course the timber sector is actually very advanced in this field, it is automated fabrication for essentially pre-digital building systems. So one could draw the conclusion that in this way, the digitalization of pre-digital design and construction approaches means that we may not really fully tap into the potential of digital technologies. So what could be a way to achieve that in the future? And this is exactly what we are investigating at the University of Stuttgart, where we think that it's not so much about the computerization or the digitalization of design and construction as we know it, but it is about how do we deal with computation and artificial intelligence to think about genuinely digital timber construction, which is actually enabled by concurrently innovating across various different areas. So I think we need to understand that the biggest potential in computation is integration. And the integration of computational design and engineering methods that enable this integration, cyber-physical robotic fabrication and construction processes to deal with this significant productivity challenge that we have in construction, and of course, then also use that to develop effective, truly digital material and building systems that enhance sustainability. And I think the most important aspect is that we do all this in feedback with each other, so that we don't look just into the individual bubble, but we need to look at it comprehensively and holistically. So integrative computation, design, and construction may allow tapping the full potential of digital technologies for truly future-proof construction. And this is exactly what we are trying to do at the University of Stuttgart, where we have a so-called cluster of excellence, which is funded by the German Research Foundation with 50 million euros to research the future of construction with 150 researchers. And I think the important aspect here is, everything I will show you is actually the work of those 150 amazing people. And they come from all kinds of different disciplines. So we not just have architects and civil engineers, but of course also researchers from manufacturing and system engineering, computer science and robotics, but also the humanities and the social science. And of course we have that coupled for two-directional knowledge transfer with a large industry consortium. We're trying to tackle these challenges for multi-story buildings, for long-standing buildings, and of course for one aspect that is also particularly relevant here in Europe, that is the dealing and building within the existing building stock. So while this whole idea about integration may initially sound a bit academic, by the way, we call this overarching holistic methodology co-design. I thought it may be more interesting for you to just look at a few examples. How can it happen? Because it's already possible. And through that, it may become a bit more tangible. So the first example I want to show you is how can we co-design or use integrative computation, design, and construction for high-performance timber structures. So buildings that actually use very little material to actually achieve high structural performance. And I will do this by showing you one of our demonstrator buildings, which is the Bugger Wood Pavilion. It's around 500 square meter shell structure, has a clear span of 30 meters, but only a structural depth of 160 millimeters. So that means it just consumes 38 kilograms of wood per square meter. Everyone that knows what a cubic meter of wood costs, despite recent rises, knows that this is not an expensive building. How is that possible? It's possible because we tune every single part to be designed to exactly meet its performance requirement. So all the parts are different, because only with that level of differentiation you can get that level of performance. And that means here we're looking at almost 380 of those roof components that make up the shell, and they all have different joints, so it's a large number of different elements. So here you can see how this whole structure is built up. It's actually made from individual pieces, and the pieces are again made from a lot of complex pieces that are all different. Overall, more than 20,000 different elements. And the interesting part is that this is a bit questioning the typical economy of construction. We're used to an economy of construction where repetition means the repetition of the same parts means that we may invest a bit more into the material, but on the other hand, it means it's more it's cheaper to build. And I think in recent times we have experienced that all of a sudden energy and materials and labor becomes expensive. So we may actually look into ways of how we can reduce the consumption of energy and materials by having a higher level of complexity in the structures. That is possible through digital technologies, because we have developed algorithms that can deal with this individuality of the elements, so they all follow the same rule, but they're all different. And at any moment in time, we know what kind of impact they have economically and environmentally, because they're part of one integrative workflow. For this building, that means we don't model any of these parts. They're actually generated, and in the generation, every single element is already included. So it's not different levels of details. Every bolt is in there from the beginning. And it's actually existing in the feedback with structural analysis, life cycle analysis, and all these aspects. And here you can see that the buildings follow rules how to find the location in which they perform best. That means we get for free a digital twin that includes also, of course, all fabrication data. In fact, what you see here, we don't need, really. That's just a geometric representation that we as architects feel quite dear to, but we could directly communicate from the algorithm to the machine. And for that, in order to really tap that potential, we also need to think about the co-design of the prefabrication process with the actual design methods. So what we've developed for this project is to say, okay, we want to have one manufacturing unit that is designed with the building that just produces the building for us. And that's possible with an actually incredibly small footprint and also actually quite a low investment. So what we developed is this robotic fabrication platform that can produce the entire building, and it's incredibly compact. So it fits onto a 20-foot container. It's actually mobile. It's registered as a container, so you can ship it anywhere on the back of a lorry or by ship, and it can produce everything. Here you can see the transportability, and we brought it to the site, actually to a local timber manufacturer, and it produces all the elements in a fully automated way. No prototype, by the way. First element ends up in the building. So how does that happen? I will explain you the production process in a second. So robot picks the bottom plate, mounts it onto the turntable on a vacuum gripper, applies the glue, puts on the rim beam, secures the rim beam with wooden nails to make sure it remains to be fully monomaterial, then applies the glue on the top, adds the top plate, and puts it in the press. Takes about 7 minutes per element. Every element is different. Every component is different. It's all run with one control algorithm that can deal with this level of non-repeatability. And you get an incredibly high level of precision. So once these elements come back, they're actually milled on the same platform with an accuracy of 0.35 millimeters. And that's, of course, important because it means that you can, this extremely high level of precision means you can build up your system like a three-dimensional puzzle in space. No scaffolding, no false work, none of all these other incredibly costly and labor-intense processes that are typically related to shell buildings, which meant actually that they disappeared from construction. And what is also important, of course, is that you have a different way of dealing with tolerances. There are none, and there cannot be any. So the last piece needs to fit. And it did. So I think what we are seeing here is a genuinely digital timber building system. That's why I wanted to show you this example. It's something that couldn't have been designed, it couldn't have been built and in a few years ago, especially not in the incredibly strict timeline of this building. So this was actually contracted, delivered, and the building opened within 13 months, yeah? Including everything. The design and development of the robotic fab platform, the certification process that is required for robotic gluing, everything. So innovation is possible also on fast track. So I think it's also a good example of how the economy of building may change to something where you say, okay, I invest more into the form, and by that, I guess less material, need to consume less energy. And that means we get an efficient structure, and in this case, if we do it carefully, also quite an expressive architecture, which for this building was a unique selling point because it was used by 2 million people as an event space, and it actually offered such a high quality of both spatial atmosphere and acoustics that there were a lot of live TV shows actually being done in this building. What is also important to say is that this building was from day one designed to be a circular building. Yeah? So you don't reuse parts, you reuse the whole building. Because this particular event architecture is actually taken down after 3 years and moves to another site. And it can do so by reusing all the parts. Not a single part is actually wasted. And I'm not just talking about the timber. I'm also talking about the cladding, I'm talking about the waterproofing, I'm talking about everything. And it will do so again after the end of its lifespan at the next site, and it will eventually become a permanent building. So here you can see this process of taking it down again. Of course, there were a lot of worries. Okay, you may get the one last piece in, but you will never, ever get it out again. It took 10 minutes with these hydraulic stamps. So no worries on that side. And here you can see how this was actually all taken down. There's no glue in the structure. Nothing is actually permanently fixed. The connections are bolted, so it can just be removed. By the way, it took 8 days for 2 people to build that structure, and it took about the same time to actually take it down. Of course, we're now looking at what are the next stages in this development. If we deal with lightweight structures, we can also think about robotic assembly. So we're developing sort of automated assembly robots that you can see here that can actually erect such a shell. That means one robot puts the building component in place, and the other robot actually puts the bolts or screws in. This is something we have actually ready to be used. So here you can see that, by the way, it's sort of run-of-the-mill hardware, but then it's actually equipped to become autonomous just by specific control engineering pieces that are added. So this is the first time we use that in construction, actually, for a building that we're currently finishing for the University of Freiburg, which is this dome structure that they use as a kind of ideas lab for their researchers. So of course, shell structures are interesting. They show the, let's say, performance capacity, but what we really need is multi-story timber buildings if you want to tackle the challenge of timber construction. And in the next example, I want to show you how we managed to transfer the same principles to, of course, what is the dominant building type in construction. So just a quick look, and I think it's interesting if you look at past attempts at industrial prefabrication and current trends in timber construction, we can see some similarities. It's not the first time that we're trying to industrialize construction. It has already been done in the 60s. Here we see the Astrid system. It was actually partially automated on-site assembly of prefabricated concrete. And I think what is interesting that we see in a lot of current attempts at serial timber construction, very similar, let's say, architectural configurations, which may offer also some food for thought of whether this is really the quality of the product that we need to be ultimately competitive. So what we did is we analyzed 350 timber buildings in a long study, 3-year study, buildings that were constructed from 2000 to 2022. And we analyzed them very carefully, the underlying grids, the way they work as a structure, the materials from which they're constructed, down to the last nut and bolt. And the result is interesting because we can see that almost 99% of those built timber building systems are, of course, based on regular and very rigid grids. So it's actually very difficult to make them fit on a complex urban site, and we need urban construction. We can also see that timber construction, 98%, has single spans. Single span means that a slab can only span in one direction. Concrete can span in 2 directions, which means you have actually very limited design freedom compared to, for example, concrete. And 3/4 of the so-called timber buildings were in fact timber steel or timber concrete hybrid structures. So not really fully timber. So what is interesting is that that means we still have quite some architectural limitations in existing timber building systems, and we need to be careful that that does not lead to the spatial monotony we know from concrete prefab. We need to make sure that we don't get limited architectural topologies, and that's the most important part, that we don't constrain future adaptability. Because a timber building is really beneficial if it's with us for a long time, but that may also mean that the use may change, because how do we know? We basically don't know for what kind of society we're designing. So what we have done is we have developed a prototype for a multi-story timber system trying to deal with the challenges. First, we don't have a solid timber system, we have a hollow timber system, which means already 40% material reduction. This is possible because we have 2 separate plates, actually fairly thin plates that are equipped with internal shear webs that you can see here, so small beams that connect the plates. And this system was from the beginning designed to be a point-supported structure, so a skeleton. No load-bearing walls, just timber columns, timber slabs for maximum future adaptability. Then, of course, we have a lightweight system, and everyone that has a little bit knowledge about timber construction will say, okay, we have building physics problems. So one of the biggest challenges is, of course, sound protection for lightweight timber structures. That typically means we have our timber structure, very lightweight, let's say 70 kilograms per square meter, and then we put all kinds of stuff on it, below it, on top of it. In this case here, 7 to 10 centimeters of cement. So we compromise a bit the resource efficiency and sustainability of the system, as you can see in the global warming potential readout on the left. We were wondering, are there not different approaches where we can address, for example, just as an example, the acoustic challenges with an integrated solution? So we just said, okay, we have those beams anyways. They are required to structurally couple the upper and the lower plate. And of course, they mean, in a standard construction, they would also mean that they're acoustically coupled. So why can we not find a way to use digital simulation to tune these elements so that they offer structural coupling, but acoustical decoupling? Turns out to be fairly simple. You just need these slits, and then actually the beams work as springs acoustically, and they can be tuned like an instrument through digital simulation, and the sound protection effect that this offers equals the doubling of mass. Yeah? So it's not insignificant. It's actually what you need to actually get away with this in a German context. Similarly, of course, we said if we go for a timber system, we want to have a monomaterial system. So no metal, no additional materials. So all the connections are monomaterial, which you can see here for this typical slab-to-slab joint, which is this, again, finger-jointed, mega finger joints, and the column head, which is typically the critical area. Don't want to get too much into the technical details, But one aspect that's important is that this was also, from the beginning, designed. Here you can see the prototypes of these two monomaterial solutions. So it's a hardwood, softwood combination. It was designed from the beginning for actually automated assembly. Yeah? Because those finger joints need to be fairly precisely assembled on site. And we do this because we also look at larger scale construction equipment, and we have this robot tower crane that can actually very precisely deliver parts from point A to point B, actually with a centimeter precision. So there's a threefold approach to that. We have research on picking and gripping the element, which means we can position it very precisely. We have fully automated transportation, including sway control. So the parts actually can be positioned within centimeter correctness. And we have the possibility to collaborate, for example, with the aforementioned spider cranes when it comes, for example, to putting the screws in for the ground-based work that can happen in a larger cyber-physical construction system together with this robot tower crane. Again, it seems to be more effort, more form, but it means less material. And again, this can be compensated for by a fully integrated digital fabrication workflow. So we have developed a prefabrication factory that can produce these pieces fully automated, as you can see here. So what is perceived as complexity is actually just dealt with by the digital technologies. This is the prefabrication platform that we have. So it's a kind of further development of what I showed you before. It's a couple of 40-foot containers now. Again, they are certified to be road legal, so you can bring them anywhere. And these platforms can actually build the multi-story timber system in a fully integrated way. So of course, the important part is that we have a digital twin that allows for an integrated design and engineering workflow. So again, the complexity of what it is required to design such a building is assisted by the computer. No one wants to deal with thousands of oddly shaped components. Here, even the layout is optimized. You get an optimized joint distribution. And in the end, all this means that we have a double span slab, and we can position the columns wherever we want. So no grid required anymore. You move the columns around. You actually have the design freedom that concrete structures offer. And that means that we have a system that can actually be used in the complex urban sites that we usually face when we talk about inner city timber structures. So in summary, what this system offers is long slabs, long span slabs, 11 meters, clear span, almost twice as much as you get in your typical timber structure, with a flat ceiling. Of course, you want to have a flat ceiling because you want to put your partition walls wherever you want. So the goal is to have this for a 150-year lifespan, so you don't want to overly constrain that by having, for example, beams or anything. Second, of course, you need to have a shallow depth. In this case, 11-meter span equals 42 centimeters with integrated acoustics and with all the design freedom that typically only concrete structures offer. I think what is important to say is that we take the research quite serious. So we also say, of course, we want to include that in the research, building a building, and this is what we're currently doing at the University of Stuttgart, is what you see here. This is the building that we're constructing for our cluster of excellence for the research, as I showed you before, and it's actually built using exactly those building systems. In the multi-story part that you can see here on the right, we have the 11-meter span, we have the opportunity to have the irregular grid. We use all this for the quality of this particular building, and on top we have 3,500 square meters of the segmented timber shells. If I tell you that this is a public building, you will know that the budget is not exuberant. With that, I hope I was able to give you kind of idea of what true integration enabled by digital technologies for timber construction sector may mean. And if you have interest to find out more, here's our website. Thank you very much for your attention.
Professor Menges, thanks a lot. I think you didn't promise too much with your introduction to the topic. One thing that struck me, and the question that I actually have to ask is, it's a total revolution of not only like a construction industry, but also wood construction industry. But if a change has to come, you always need a tilting point, like in history. You need enough pressure to actually have that tilting point to make the technology scale. So would you say we are at that situation right now? And or what do you think it still needs for the technology to scale?
So I think that the technologies in and of themselves may be positively disruptive, but maybe what is really disruptive right now is the situation we're facing, no? The situation we're facing is materials become incredibly expensive. Energy becomes expensive. There's all this uncertainty, which means risk, which means higher cost in construction, which means people stop constructing. On the other hand, we need 400,000 new residential units every year just in Germany. So I think there is a situation where I would say the disruption comes from the context. It's actually required. I mean, even if we just say we take the Paris Agreement serious, without a change in the construction sector, it will just not happen. That's the truth. And at one point, I'm sure, not just the insiders as within this room may wake up to this, but also the larger political situation. And then I think we will see that change that we also saw in other sectors like mobility.
Perfect. Professor Menges, thanks a lot.
Thanks.